Doing every challenge question, part 55. This is all the mechanics in the entirety of year one. We start with a velocity time graph. It changes direction when the velocity goes from being positive to negative, which is after 6 seconds. The total distance traveled is just the area under the graph. It doesn't matter if the graph is down here because distance doesn't care about the thing coming back again. It's just total distance traveled. If you walked 10 meters forward and 3 meters back, that's 13 meters traveled. So you just work out all these areas and add them together. Displacement is different. If you walk 10 meters forward and 7 meters back, you've only traveled 3 meters according to your displacement. And so therefore, for 6 seconds, we're just going to still use this number 10.5. And for 10 seconds, we're going to take 10.5 and take away this 6 that we were traveling back towards ourselves for. Speed time graph, so it looks the same here and here, just going faster than going the same speed. Then it's going slower until it has velocity 0, which is the same as speed 0. And then it actually, if you're doing speed, you just don't care about the direction of the velocity, so you're just going to go back up to 2, which is lower than this 3 was up here, and then just across again to finish up. Probably should have labeled some axes, but I couldn't be bothered. Next one then, a particle moves in a straight line from A to B, starting speed 3 or velocity 3, finishing speed 5. Get out the Suvat equations. We don't have anything about acceleration, but we do seem to care about t. And we also seem to care about s at some point. So I think this might be the equation to use. Let's go with s equals a half 3 plus 5 times t. And now the next particle leaves a second afterwards and travels the same distance s from A to B, which I'm just calling s, and has initial velocity and final velocity. So the same formula again used would be good. This, by the way, cleans up obviously to just 4t. But for the next one, we're going to do the same thing. It's going to be a half into 4 plus 8, and then it leaves 1 second after, so we're just going to have time t minus 1. And we clean this up, and we get this, and then of course the s's are the same because it's traveling from A to B, both of them, so therefore this equals this. Solve for t, and then you put t into here, you solve for s, and you have the question done. This is very similar. We have a particle projected upwards with the speed of 12, so downwards we're going to have acceleration minus 9.8. We're going to have another particle projected up with a speed of 20, and at some point, the two things are going to collide. So this one is essentially going to catch up to the one that was fired first, but slower. So let's get out to Suvat equations. We know A this time, so we're not going to use this one down here. We're probably going to use this one here, I think, a couple of times, because we've got, I mean, S, the position where they collide is the same for both of them. So the S will be the same for both, because we're only interested up to the point where they collide. So I think S is this for the first one, initial speed 12t minus 9.8. And for the second one, it's going to look like this, because the speed is 20, and it's fired again 1 second after. So we're going to keep this adjustment of t becoming t minus 1. And otherwise, it's the same. The s is the same for both because they're going to collide at the same height above here. I'm taking upwards to be positive. If I just set this equals this and then do a bunch of expanding out, a bunch of solving, we eventually, it's quite kind so that the t squareds cancel out. You get t as this. So they collide together after 1.4 seconds. We can shove that 1.4 into this formula here to find the s, and we'll get that they collide 7.18 meters above where they were fired from. Another question that's very similar, we're going to drop a stone, which means its initial speed is 0, because you just sort of drop it. You don't throw it down. You just drop it. And then another one is thrown down with a speed of 25. Both reach the floor, which is maybe h away from where they were thrown, at the same time. So I think this sounds like basically the identical question. We're going to use this with u's known and with a minus 9.8. The t is going to be the same because it takes the same amount of time, except it doesn't, right? 2 seconds later. So for the first one, the t is just going to be t. So it travels h, because that's why I just called this, in this initial speed 0. The second one is going to be exactly the same, but with t minus 2, and with the initial speed 25 instead. Again, just set these two things equal to each other. You get this, you start solving for t, you get t as this, and then you can put that t into either of one of these, it doesn't really matter, and you end up with h is 155 meters high. Another one that is very similar, you have a board projected vertically upwards, speed 10, and then, which is 50 meters above the ground, I guess, and then you have another one that's dropped, so again, velocity 0, dropped downwards, and the balls collide 25 meters above the ground. So basically, we're 50 meters above the ground when we throw this one and drop this one, and this one goes up and down and catches up to this one, and they collide 25 meters above the ground. So okay, this is going to be very similar. We're going to use s equals ut plus alpha dt squared again, because you've got the u, we've got the a. The t is going to be this, not the same for both. Again, it's going to be adjusted with like a t and a t minus big T maybe. Except I think we can get around any of those complicated issues by just finding how long it takes this one here to drop to 25 meters above the ground. So it's s is minus 25, it's dropped 25, initial speed 0, we're just using the same formula we've used a couple of times now. We get t as this. So that's how long it takes this stone to reach here, which means it's the same amount of time that it takes this one to go up and down and reach here. S is still minus 25, remember, because it doesn't care about this displacement. It doesn't care about going up and down again. So the initial speed is 10, and then we have this. We can solve for t here. This t is different to this t. This t represents the time that it takes this stone to go all the way up and all the way down. And what I'll look for is I'll look for the difference between these two t's, because that's the amount of time after this one was dropped. So we solve for this t, we get a couple of values. We obviously don't care about this one. And then we find the difference between the two, and we must have paused for 1.23 seconds, which is big T, before moving on to that thing. Cool, some different questions then. So we have a force here, we have a force here. The resultant force is obviously in this direction. You can just pick up this force and put it over here. And you're told that it's 60 degrees away. So therefore, I think we have a triangle here of A and 10. So I think we have tan of 60 is A over 10, which means tan inverse of 60 is A over 10, which is root 3. And so A is 10 root 3. And the magnitude is just going to be 10 squared plus 10 root 3 squared square rooted. And that'll be all that she wrote. You just need to put it in a calculator. This question's kind of cool. We have a stone mass 0.4 kilos is what we need to use. Now it's in a pond full of water, so our accelerations are all essentially going to be messed up here because we have a constant resistance of 3 newtons. So that's always opposing the direction it's going. So if we fired it upwards with speed 10, that magnitude is downwards with 3. So it's always opposing the motion. I've been lazy here making this an acceleration, this velocity, despite looking the same, but I kind of know what I'm doing, so I'm just doing it anyway. We also have, of course, have a force going downwards of 0.4 g. And now we can use F equals ma here. With these two things being the F, taking downwards to be positive, this being the mass, we can work out A. And now that we have A, we can do suvat, and I think we can just use, well, we don't have anything about time, so I think this will be the equation to use. When this thing reaches maximum height, which is what being asked for, that means that its final velocity is 0. So we can just use this equation and do this. I think I'm now taking down to be negative, apparently. I don't know why I did that, but in any case, we get S as this, and that will be our greatest height. The speed of the stones that hits the bottom. Now, initially you might think, well, that's just 10, right? It goes up and it goes down. It's just going to be the same as what I started with. But because this force here changes direction, because remember, this 3 always oppose direction. So if you get to the top, and you're essentially, again, like we saw earlier, being dropped from the top downwards, this 3 newtons is now, because the thing is going to be moving downwards, acting upwards. The 0.4 g is still acting downwards, but now we've got this imbalance, which means the acceleration is different on its way down. So again, force equals ma. I think I've taken upwards to be positive now for some reason, and we get a is equal to this, so it's accelerating downwards with 2.3. We can now just use this formula again over probably this one, right? Because we want the final speed. We have the initial speed of 0. We have 2as. So we'll get v as this. So that's the speed it hits the ground. And now the total time taken. I think I can just use v equals u plus at. I have the final speed. I have the initial speed. I have a. I just need t. So I can work out the time taken to do the downwards bit. It's just this. To do the upwards bit, so we'll go back to this situation. To do the upwards bit, I think we can just use v equals u plus at again, because we have final velocity 0, initial speed 10, and we have a is 17.3. We can just work out t. We get this, we can add the two t's together, and we end up with this on the end. Good. We have our next one then, so it's probably more force equals mass times acceleration stuff, it looks like. F1 is this, F2 is this, particle acceleration like this. So our resultant force in the eyes is minus 4 plus k, or k minus 4, as I've written, doesn't really matter. And the j's is just 2k. So that's the resultant force, just adding these two things together and putting the i's and j's together. Now we know that the magnitude of acceleration is 8 root 17. So, or first actually we need to do F equals ma, don't we? So 0.5 is A is m, F is not this, but what we can do is we can say F is this, and then because we only have the magnitude of acceleration, we can work out the magnitude of this before we do it. I've doubled everything just to get rid of the 0.5, and now I know the magnitude of this is 8 root 17. So I can work out the magnitude of that and just say it must be 8 root 17. You can square out both sides to get 64 plus 17 over here, and you can square out this as well. Obviously use double brackets for all of this. Remember, this is a 16k squared, not 4k squared. Put everything together, divide by, 4? This ends up being a thing that you can put in a calculator. You write it twice just for fun, and then you end up with k is 8 when you solve it. Good, so you don't need the -1. Obviously, I think it said that k was a positive constant. It did. So we've got another one here. We've got two boats starting at different points on a river, constant force of 3I. So let's work out some resultant forces. So for boat A, the resultant force is add the i's together for -4, and then add the j's together for 2. So that's the resultant force of A. Resultant force of B, add the i's together for 3 plus k, add the j's together for just 1j. The boats are accelerating in perpendicular directions. So the acceleration is directly is in the same direction as the force that is acting. So the acceleration of these two objects is the same direction as the resultant force of these two objects, which is what we've got here. So this may as well have said that given the boats have resultant forces in perpendicular directions, it may as well have said that because it's the same thing. You always accelerate in the direction of the force. So okay, this one goes over this way because it goes -4 and then up 2. So it's going this way, and we can just think of the gradient as being -1/2. And now this one here, if you draw a similar triangle, it goes k plus 3 across and 1 up. So the gradient is 1 over k plus 3. And now for two gradients to be perpendicular, you just multiply them together and you get -1. We can cancel the minuses, we can double everything, or we can put the 2 there. It doesn't matter. Cross multiply, solve for k, and you get k as this. And we're all done. To the more interesting calculus questions, I guess, we just want the distance. Our very first question was the same thing. It's just the area underneath this curve here. All I need to do is work out what x value these two curves meet at, which is this k value here, which they haven't told us when the curve changes definition from this to this. But we notice that they meet at the same point, so we can just set these two objects to each other to find this point of intersection. If we do this, I think I times everything by 12, and then I rearranged, and I got a quadratic, and I got t was 4. It's obviously not this, so t is 4. So to work out the distance, or the area underneath this, which is the distance, I'm going to integrate this curve between 0 and 4, which is this one, and then I'm going to add on the integral between 4 and 10 of this curve here. Very easy maths here. Just do a couple of integrals. There's nothing complicated. Put the numbers in and type it on the calculator, and you get your answer. The next one then, particle starts at rest, moves in a straight line. We have acceleration this. Let's immediately integrate that for the velocity, like so. We've got a plus c, except it starts at rest and goes, so when t is 0, v is 0, I guess, so c is 0. And now, the only thing we need to be careful of here when we're trying to find the distance traveled in the first 5 seconds is it's asking about distance traveled. We saw this in like the very first question. If you walk forward 10 meters and then walk back 5 meters, your distance traveled is 15. Your displacement is only 5. And the problem with just integrating velocity between 0 and 5 is, by definition, the integral of velocity is displacement. And that's not what they've asked us for. They've asked us for distance. So what we need to do is we need to check that at no point does this ever turn around and start going back the other way. And if it does, then we need to break the integral there and then add it onto the rest of the integral afterwards and make sure we're just adding on a bunch of positive numbers together. So let's find out when this velocity is 0. We can do that by factorizing and factorizing again. We end up with t is 0, t is 4, and t is 5. So the bad news is this does change direction in the first 5 seconds. After 4 seconds, the velocity is 0, and it starts going backwards before it goes back to 0 again at t is 5. So what we have to do is we have to integrate between 0 and 4, and this will find the total distance traveled in the first 4 seconds. So I guess we can do that. We get this, and now we can integrate between 4 and 5. I'm expecting this to give us a negative number because, again, this integral is trying to find displacement, and we've just decided because the velocity is now negative, we're going backwards. So this should give us a negative number, which it does. We don't care about this negative number. We're just going to add the positive version of it to this to find a total distance traveled of 32.75, sorry. Another one then, so very similar. Let's find v immediately. Now, there's a plus c here. I think we're supposed to assume that c just has to be 0, although I don't think it matters a huge amount because the integral between 4 and 3, because in the 4th second is between 4 and 3, is 50. Now, again, if this thing changed direction somewhere in there, then this doesn't work. But if it changed direction at some point, I don't think there's a way of doing this. So we're just going to have to assume that it doesn't change direction at this time, which is dumb. I don't really know what the way around that was meant to be. I also don't know why I've put a plus c in here. Oh, of course I know why I put a plus c in here, because I think I'm trying to solve for c. That's the whole point. Of course it is. Anyway, you integrate all this together, put the 4 and the 3 in, and you solve for c, like I've been saying. Get c as 6, you put c as 6 back in here, and now you can actually find the velocity when t is 5. Again, I didn't think it was a very well-written question, just because we had to make this assumption that we had no right to make. Anyway, a tram starts at station 1. This is a really interesting question. There's a lot of information they give you, and it's not easy to see where it all connects together. And we're going to have to do a lot of SUVAT and a lot of other things as well. So firstly, we cover a distance of this in period t1 with some kind of constant acceleration, and we get to a constant speed of v. Now, I think the most useful way of writing that is this formula here, where t1 refers to the t1 they've given us, and a1 refers to the acceleration that they haven't really talked about at all, that I'm going to plan to try and get rid of later. But I think that's just me using this formula here. It starts from rest, of course. So this is 0. So that's all good. I think I just doubled everything and wrote it like this. Next, we have a constant speed v for t2 seconds going this. We can just use speed equals distance times time here. Sorry, speed equals distance over time, for therefore distance equals speed times time. So that's that information. This next piece of information is just not helpful. Tram then decelerates for t3 seconds and comes to rest. Doesn't tell us anything about the distance or the acceleration or how long it takes, aside from it just being t3. So that is completely useless at the moment. We have to think quite carefully about how that's going to be helpful. What we can also say, though, is that we can connect the first two things together, because the final velocity of this first thing, where it accelerates to, the velocity it accelerates to in this first t1 seconds, is this v here. So what I can do is I can use this formula again, where this v, which is the final velocity in the first thing, which is the same as this v, because that's the velocity it gets to before doing the second thing, is equal to 0 because it starts to rest, plus at, where at is these first two things here. So I've also got this formula, which is just v equals a1 t1 to use. And now I have some more things down here about the t's. 7 minutes is 420 seconds, so all the matter for this. This is also here. And yeah, now I need to somehow work through all of this information to get something useful out of this. I have quite a few unknowns. I have 1, 2, 3, 4, 5 unknowns, is that? Or is it 6 with the v? Did I count that? Got quite a few unknowns. Anyway, let's start working towards some things here. So this one tells me 3,500 is a1, t1, t1. But a1, t1 is v, so that means 3,500 is v, t1. So that's the first thing I did. And then I decided to divide these two things here, which cancels out the v. This divided by this is 5, and then we get t2 over t1 is 5. Cross multiply, and you get t2 is this. And now I have 3 unknowns and 3 equations down here. So I think this is all good to go. I'm just going to, how am I going to solve this? I can't remember. I'm going to substitute them all in for t1s, right? So keep the t1. This is the same as 5 t1. And then this is the same as 3/4 t1. We can now solve for t1. I don't know why I did that much work. Also, I was doing this in a phone calculator, which is why you see all these mixed numbers, because my phone doesn't do anything else. But yeah. Anyway, t1 is that. So now we can use that to work out t2 from here. So just times it by 5. So gross. And then what do we do here? Times by 3 and then divide by 4, I guess, or whatever. And you get t3 is this. So okay, that's all the t's. So that's all that done. And then the distance between station A and station B. So that's the total distance where we have these two bits. So we just need the third bit from this previously useless piece of information here. So okay, we can set up some SUVAT with that. We can say v, the speed that we were going that whole time based on this equation is this divided by t2. So I typed that into my phone and got this. And then we can use that v to work out the distance that this goes, because we can use s equals a half. U is this one here, because that's the speed that we started decelerating from. V is obviously 0 because we finished at the train stop. And t is this time that we do that final period of deceleration in. And we'll work out s is this thing here, which we add to this list and get this as our final answer. Just a really interesting question, I thought. Lots to do. It was fun. I've talked about these kind of questions in a video before. I hate these pulley questions with the masses in them. I draw it like this. Firstly, I typed this entire question in wrong because I didn't read this. I don't know why they do this sometimes. Completely pointless, and I hate it, but sure. So that just forced me to retype the entire thing. So we have a mass of some blocks. We have a resistance here of 2 newtons. We also have, of course, this is a force of 2 newtons. We have a force of, from C, 10 g down, and from B 5g down. So there's those two forces. Like I said, I don't like this kind of picture. I prefer drawing this. This is just as if I'm imagining everything to be cars and caravans and pulling things. And we have A connected to the pan, which you do need to draw as an object if you're going to do this. These tensions refer to the tensions in this string. Then you have the next thing that the pan is lifting is C, so that comes next. And these forces here, which I haven't bothered to label because they didn't ask me for them, is the reaction force between C and the pan. And then C is essentially carrying B, which is this, and therefore these forces here are the reaction forces between B and C. Feel free to do questions like this if you just prefer the car caravan setup like I do. This picture gets us everything done here because now we can just do F equals ma on the entire picture. By the way, this is almost, these 10g and this 5g, almost acting as like resistance of the motion to the car and caravan, and this is almost acting as the driving force, I guess. I don't know. Anyway, the thing is going to be going this way because these forces are bigger. But anyway, F equals ma on the entire system says that if I take left, I'm going to probably take right to be positive, right? Yeah. This force plus this force minus 2 is equal to all the masses, which is 20 times A. We can work out A as this. And now we can work out the tension in the string, which is this actual tension here, because that's actually the string. We can cut the diagram here to say that 2 minus T1 equals 5 times A, I guess, or the other way around, depending on which way you're taking positive to negative and so on. T1 is this. And now the magnitude of the force exerted by block B is essentially this tension here. So let's cut the diagram here and just consider 5g minus T2 equals 5 times A, which we know is 7.4. Again, taking all these g's to be 10, you work out T2 is this. What came next? The magnitude of the force exerted on the pulley. So we've got a force here of 39 and a force here of 39, which I didn't draw into here, but I did have here. The resultant force is like in this direction downwards like this. You can just imagine putting this 39 down here, which is something we did in like the very first question. Anyway, this force is going to be 39 squared plus 39 squared square rooted, which is this. And I use the fact that the string is insensible to say that, or I assumed that the acceleration in all these objects is the same. Otherwise, this wouldn't work. Thanks for watching. I'll see you next time.